Hello everyone, my name is Niketan Dobaria and here we are discussing basic electrical engineering in which we are discussing chapter number 1, that is DC circuits. And in our previous video we have discussed two theorems, superposition theorem and Norton's theorem to solve any circuit. Here in this video we are going to discuss our next theorem, and that is Thevenin's theorem. Before we start Thevenin's theorem, again let me remind you why we are discussing theorems over here, or what is the use of theorem. In simple language, we use or apply any kind of theorem, Thevenin, superposition or Norton, to simplify or to find out the particular parameter of any complex circuit. As an example, you can find out the voltage or current of any particular branch in any complex circuit easily. That's why we are using various theorems over here. Let's start. What is Thevenin's theorem? Here we have a statement of Thevenin's theorem, and it's in linear active network. The current flowing through any element can be found by replacing the remaining part of the network by a equivalent voltage source that is going to be defined by VTH in series with a resistor which will be known as a RTH, Thevenin's equivalent resistance. So basically what we are going to do over here, let's say here if we want to find out the current, or you can consider voltage also. If you want to find out the voltage or current of any particular branch, and let's say that is a load resistance or load branch. So what can we do over here? We can replace all network which is connected with that particular branch or load branch by a simple equivalent circuit in which there will be a voltage source in series with a simple resistor. So that is nothing but a Thevenin's theorem. Another example here that is shown over here. Here we have a one load resistance that is connected across some network. So this box is representing any kind of network. Now if we want to find out the voltage or current of this branch, as I mentioned, we can convert this complex network into a simplified diagram where we will have a voltage source and resistance in series, and that voltage source will be defined by this VTH value, Thevenin's equivalent voltage, and that resistance will be defined by this RTH, Thevenin's equivalent resistance. So that is shown in this given circuit diagram over here. As you can observe over here, this box is replaced by a voltage source and a series resistance. So this is explanation of Thevenin's theorem. Now, next we will discuss the method or steps to derive the simplified circuit or its equivalent circuit diagram of Thevenin's equivalent circuit. And for that, let's consider again same diagram over here. We have a complex network which is connected with this load resistance, and we want to have the equivalent circuit of Thevenin's theorem. And for that, let's start with this step number 1. What we will do in step number 1? In step number 1, we will remove the load resistance. That means here in this diagram we have a load resistance over here across this A and B. So first of all, we will remove that load resistance and we will consider this A and B as an open circuit terminal. Now, in next step number 2, here we have A and B as an open terminal. Now in step number 2, we will find out the voltage across this A and B, and we will define that voltage as an open circuit voltage, or VTH, Thevenin's equivalent voltage. And for that you can use KVL, KCM, voltage divider, current divider rule, which were discussed previously in our previous videos. So that will provide the value of VTH that is going to be over here. Now in our next step, in which again we will consider this A and B as open terminals, but now we will remove all sources which are presented in this network over here, as we are discussing superposition theorem. When we will replace any voltage source we will replace it by short circuit, as we consider that its internal resistance is approximately or almost zero. Same way, when we will replace any current source, or when we will remove any current source, we will replace it by open circuit. Why? Because we are considering that internal resistance of current source is almost infinite, and that's why we will replace it by open circuit. So by considering this, we will remove all sources from this given network. So basically we will have a only resistive network, and we will measure its equivalent resistance with reference to this AB terminal, and whatever will be the resistance that will be defined by this RTH, Thevenin's equivalent resistance, and we will put value of this RTH or that RTH resistance in series with this VTH, so that will form equivalent circuit diagram of Thevenin's theorem. So basically this circuit portion, which is in dotted box, that is nothing but a Thevenin's equivalent circuit. So again, let me remind you what is VTH, that is Thevenin's equivalent voltage source, RTH, that is Thevenin's equivalent resistance, and this circuit or this portion where VTH and RTH in series, that is known as a Thevenin's equivalent circuit. Now, in our next step, what we will do, we will connect a load resistance across this terminal A and B, and when this load resistance will be presented over here, this load current will flow through this load resistance, and at that time or in this circuit, we will find out the load current. Now, basically, we have a simple circuit over here. Basically, we have a two resistor in series, so we can find out the current of the series connection, or I can say load current by this given equation. IL is equal to VTH divided by RTH plus RL, which is load resistance. So these were the steps which will be followed to simplify any circuit, to solve any circuit when we will apply Thevenin's theorem. Next, we will consider one circuit diagram over here, and in which we will apply Thevenin's theorem, and we will find out the one branch current for a specific resistance over here. As an example, we have one circuit diagram over here in which we are going to find out the current of this 20 ohm resistance which is connected across this AB terminal. So let's start the example. And in step number 1, first of all, we will remove the that 20 ohm resistance which is across AB. So here we have to remove the 20 ohm resistance, and next, we will find out the voltage across that AB, and that is going to be VTH. So let's find out the voltage across this AB now, and that is going to be VTH across this branch CD. Now, as we are measuring voltage across this AB, but this is open circuit, so there will be no current through this 10 ohm which is across C and A. So there will be zero voltage across C and A. So if you measure the voltage across AB, or if you measure the voltage across this CD, that is going to be same. So basically here we are going to measure voltage across the C and D. So that will be defined VTH over here. And for that, first of all, we need to find out the total resistance across this battery. So, first of all, if we measure the total resistance across this battery, and for that, if we observe the diagram over here, this 10 ohm and 10 ohm is going to be in series connection, and this series connection is going to be in parallel connection with this 10 ohm. And again, this circuit, whatever will be the equivalent resistance of this circuit, that is going to be in series connection with this 10 ohm. If we want to measure the total resistance across this supply voltage, so equation of that is going to be this 10 plus 10, that is going to be 20, and in parallel with this 10 ohms, here 10 in parallel with 20, and this is going to be in series with this 10, so plus 10, and answer of this is going to be 16.67, and that is going to be total resistance. So now we have a total resistance, and based on that we can find out the total current, and that is going to be I is equal to V by R. Basically this 20 by this 16.67, and that is 1.2 ampere. So up to now we have a total current through this branch which is flowing from this 20-volt source and this 10 ohm resistor. And now this total current will be divided in this two branch, and we need to find out the current through this branch E, C and D. And for that we can use the current divider rule at this terminal E. So if we apply current divider rule at this point E and find out the current through this branch ECD, so that is going to be as mentioned in this given equation over here. Now current ICD, that is going to be total current, means 1.2 into next resistor, that is going to be 10 ohm, divided by the both addition of both resistance, means 10 plus 20, or you can say 10 plus 10 plus 10 means total 30. So here we have an equation, and that provides the equation of ICD is equal to a value of ICD is equal to 0.4 ampere. So basically now we have a current of that CD branch, and if you want to find out the voltage across that CD, so that is going to be V is equal to I into R. So that will provide a VTH, means I into R means 10 into 0.4. This is R into I. So that will provide the 4 voltage. So this is the VTH voltage across CD, or you can say voltage across AB, VTH 4 volt. Now in next step we are going to find out the RTH, and for that here we will ignore all sources over here. So we have a 20-volt source over here. So we are replacing that source by this short circuit branch. So that will provide the purely resistive circuit over here. And now if you measure the resistance across this AB, so to find out the resistance across this AB, let's start from over here. Now this 10 ohm and 10 ohm are going to be in parallel connection, and this parallel connection is going to be in series connection with this 10, and this wall connection is going to be in parallel with this 10. Again this will be in series connection with this 10. So if we want to find out the total resistance of this network, so that is going to be 10 parallel with 10, so that is over here. Again that is in series with this 10, so here plus 10. Again this total resistance is in parallel with this 10, so again that is in parallel with 10. And lastly this wall connection is in series with this 10, so plus 10 over here. Now if you simplify this 10 parallel 10, that will provide 5, so 5 plus 10 over here. Now that is again with parallel 10. Next 5 plus 10, that is 15, that is parallel with 10, so 15 parallel 10 plus 10 as it is, and 15 plus 10, so that will provide the 6 ohm, and plus 10, so that will provide the total 16 ohm resistance. So that defines the RTH. Now we can put the value of VTH and RTH in equivalent circuit diagram. So that is over here where VTH is equal to 4 volt, RTH is equal to 16 ohm, and load resistance was 20 ohm. So that was connected across this AB. Now from this equivalent circuit diagram, we can find out the load current IL. So in step number 4, we will find out the load current IL, and that is going to be total current IL is equal to VTH by divided by this RTH plus RL, that is given in this given equation. Load current or total current is equal to VTH divided by RTH plus RL. If you put all values in this given equation, so that is going to be 4 divided by 16 plus 20, so that will define 0.11 ampere. So this was the method how we can find out the load current or any branch current. And same way you can also find out the branch voltage or load voltage for specific branch. So this was the example based on Thevenin's theorem. Thank you for watching this video.